Hello, welcome to session 4 of data communication. Today we'll be looking at transmission media. Now, transmission medium is the physical path, like we saw in the other slides, between the transmitter and the receiver in a data communication or a data transmission system. Now, this transmission media can be classified as guarded or unguarded. Now, with guarded media, the waves are guarded along a solid medium. We are looking at copper twisted pair, we are looking at copper coaxial cables, we are looking at optical fiber or fiber optics. Then we have the atmosphere and other space, which are examples of unguarded media, what we term wireless. And this form of transmission is referred to as wireless transmission. This is a block diagram of the transmission media. So we have broken down into guarded and unguarded. Then for guarded, we have the twisted pair cable, we have the coaxial cable, we have the fiber optic. We'll take each of these medium and speak to them or speak about them. Then we have the unguarded media, which is wireless or free space. Now, in the design of data transmission system, our key concern has to do with data rate and distance. Now, a number of design factors relating to this transmission medium and to the signal determine the data rate and distance that needs to be used. Now, we've already looked at bandwidth, but here, one of the design factors we want to consider is bandwidth. Now, the greater the bandwidth of a signal, the higher the data rate that can be achieved. And we can even say the faster data is being processed. Then we are looking at the transmission medium. It also plays a key role in design of our transmission system. We've already looked at the impairments such as attenuation that limits the distance or due to distance. But for guarded media, twisted pair suffers more impairments than coaxial cable and optical fiber. Another design factor is interference. This is interference from competing signals in overlapping frequency bands that can distort or wipe out a signal. Then the number of receivers that we use or that we have. Now, a guarded medium can be used to construct a point-to-point link or a shared link with multiple attachments. Now, for guarded transmission media, the transmission capacity in terms of either data rate or bandwidth depends critically on the distance and on whether the medium is point-to-point or multi-point. Now, I want to take each of these media and say something about them. Now, we have the twisted pair, the least expensive and most widely used. This consists of insulated copper wires arranged in a regular spiral pattern. Now, it's most commonly used in our telephone networks and is the workhouse for communications within buildings. And twisted pair may be used to transmit both analog and digital signals, and it's limited in distance, bandwidth, and data rate. Like I said earlier on, twisted pair can take up to about 100 meters of cable length. Coaxial cable. Now, coaxial cable, unlike twisted pair, consists of two conductors, but it's constructed differently to permit it to operate over a wide range of frequencies. Now, this is used in a wide variety of applications. We are talking about our television distribution. We are talking about long-distance telephone transmission. We have short-run computer system links. And even for our local area networks, it's also used to transmit both analog and digital signals. Our next medium has to do with optical fiber. And optical fiber is a thin, flexible medium capable of guarding an optical ray. It's as thin as from 2 to 125 micromillimeter, and it's already enjoying considerable use in long-distance communication. Now, its use in military application. Its use in military application is growing over time. Gone are those days, less of optical fiber was used, but now we see our military giants all using fiber optic for their data transmission. This transmits a signal encoded beam of light by means of total internal reflection. And the following characteristics distinguish optical fiber from twisted pair or coaxial cable. It has greater capacity, it has smaller size, it has lighter weight, and has low attenuation. It can go for several meters of cables. The next transmission we want to look at is wireless transmission, and there are three kinds of frequencies that we are interested in with regards to wireless transmission. Frequencies in the range of 1 gigahertz. So 1 gigahertz, which is equals to 10 gigahertz to 40 gigahertz, are referred to as microwave frequencies. Then we have the frequencies that are in the range of 30 megahertz to 1 gigahertz. And these are suitable for omnidirectional applications, and these are referred to as radio range. Then we have the last frequency range, which is used for local application, and this is known as the infrared portion of the spectrum. This covers roughly from 3 times 10 raised to the power 11 to 2 times 10 raised to the power 14 hertz. Now, for unguided media, transmission and reception are achieved by means of the use of an antenna. Now, an antenna can be defined as an electrical conductor or system of conductors that are used either for radiating electromagnetic energy or for collecting electromagnetic energy. In two-way communication, the same antenna can be used, and it's often used for both transmission and reception. So the receiver and the transmitter get to use or are being used by just one antenna. Now, there are categories of wireless transmission. The first one to look at is the terrestrial microwave. Now, the most common type is what is known as the parabolic dish. A typical size is about 2 meters in diameter. The antenna is fixed rigidly and focus a narrow beam to achieve a line of sight transmission to the receiving antenna. Now, this is used in long-haul telecommunications services as an alternative to the coaxial cable or optical fiber. We see this at or the telcos make use of this at our offices. We see very big dish sitting outside the office, and we wonder what these are. These are terrestrial microwave, and the higher the frequency used, the higher the potential bandwidth, and therefore the higher the potential data rate. The common frequency used with regards to terrestrial microwave are in the range of 1 to 40 gigahertz. Then we have the satellite microwave, and this is used to link 2 or more ground-based microwave transmitters or receivers, and these are known as the earth station or the ground station. And the most applications for satellites are for television transmission. So we have our DSTVs, we have our Strong, we have our Go TVs, all making use of these satellite microwave. And long distance telephony or telephone transmission, private business networks also use this, and global positioning also makes use of satellite microwave. Now, the optimum frequency range for satellite transmission is in the range of 1 to 10 gigahertz. Then we have the broadcast radio. The principal difference between the broadcast radio and the microwave has to do with the omnidirectional and the directional part of it. So the broadcast radio does more of omnidirectional, and the microwave does more of directional transmission. And it's used to encompass frequencies in a range of 3 kilohertz to 300 gigahertz. And this covers FM radio and UHF and VHF television. We get to see this when we are doing our TV settings. Then we have transmission, or transmission is limited to the line of sight, and distant transmitters will not interfere with each other due to reflection from the atmosphere for the range of 30 megahertz to 1 gigahertz. So there are 3 categories. We have looked at the terrestrial, we have looked at the satellite, we've looked at the broadcast way of transmission with regards to wireless. Now, a signal radiated from an antenna travels along one of 3 routes. We have the ground wave, we have the sky wave, then we have the line of sight. Now, with the ground wave propagation, this propagation follows the contour of the earth and can propagate considerable distance well over the visual horizon. Now, this effect is found in frequencies up to about 2 megahertz. And the best known example of ground wave communication is what we have, the AM radio. We hardly use the AM radio. What we use is FMs, or we use the FM radio. Then we have the sky wave propagation. This is used for amateur radio, CB radios, and international broadcasts such as BBC and Voice of America. With this propagation mode, a signal can be picked up thousands of kilometers from the transmitter. We get to see this in the Al Jazeera and the BBC News during the war crime scenes. This skywave propagation is what is being used. Then we have the line of sight, and this is about 30, or this is above 30 megahertz. Neither ground wave nor skywave propagation nodes operate. So the communication must be by line of sight. It means that if I'm communicating to the dish, I should have a clear sight to the dish, no interference of whatsoever, using trees and all that interfering in sound. We need a direct sight or line of sight. So for ground-based communication, the transmitting and the receiving antennas must be within an effective line of sight of each other. A transmitted signal attenuates over distance because the signal is being spread over a larger and larger area. And this form of attenuation is known as the free space loss. Now, additional loss between the transmitting and receiving antennas is known as the atmospheric absorption. So another impairment is known as multipath, where we are having different paths which signals travel. Now, signals can be reflected by obstacle so that multiple copies of the signal with varying delays can be received. So once an obstacle comes in between our signal, this reflects our signals, and this gets to move in different directions, but are all converge at one point. Then we have refraction, which is caused by the changes in the speed of the signal with regards to altitude, or by other spatial changes in the atmospheric condition. And this brings us to the end of section 4. I'll see you in section 5.